Okay, in this video I'm going to continue on my tutorials on thermodynamics and statistical mechanics. This is video number 35 and I'm going to discuss the thermodynamic identity. I'd like to draw your attention to my website universityphysicstutorials.com. So in actual fact there are two thermodynamic identities. One is for mechanical equilibrium and that's the one we're going to talk about now, and that's why this is video number 1 of 2. The second one is diffusive equilibrium and I'll talk about that in video number 36. So the previous videos to this which are relevant are number 28, where I discussed entropy versus energy graphs, and number 25, where I discussed the second law. So to be honest, I'm going to do a bit of revision with this in order to talk about our thermodynamic identities. Now the reason the identities are so important is that they relate infinitesimal changes in each of the fundamental quantities, and that's often what we're looking at. So let's talk about the second law. The second law says that spontaneous flow of energy stops when the system is at or near the the state of maximum multiplicity. And the reason this spontaneous flow of energy stops there is because the system is in its most likely macro state. And because we know that the entropy is equal to k times the natural logarithm of our multiplicity, we can paraphrase the second law by saying entropy always increases. So in the video where I discussed entropy versus energy graphs, what we saw is that when we had two systems, they were observed to be in equilibrium. They were observed to be in equilibrium when del S total del U sub, we'll say, system A was equal to 0. So when the entropy of the whole system with respect to, we'll say, any one of the particular system's energy was equal to 0. Now, we need to look at what entropy is. So we know, or just we'll say the mathematical properties of entropy. So the total entropy is going to be k times the natural logarithm of omega max. Okay? Or we'll say, well, omega max, that's fine in a specific case, but the total multiplicity. Okay? So that's k times the natural logarithm of the product of their multiplicity, something we've spoken about in the past. And then we're going to have, due to our logarithmic identities, we're going to have the k times the natural logarithm of A plus k times the natural logarithm of B. Now, of course, this is the entropy of A, and this is the entropy of B. Now, you might be saying to yourself, well, so what? Who cares? The point here is we're able to sub the fact that we've S total is equal to S sub A plus we have also S sub B, like this. Okay, that is the total entropy. So if we plug that into our equation here, that means what we're going to get is del S sub A del U sub A plus del S sub B del U sub A. I need to note this, by the way, that it's with respect to only one of them is going to be equal to 0. Alright? But we also know that del UA is equal to minus del UB. So basically we're able to sub in, and we saw in the past that we were able to get the following relationship. Del S sub A del U sub A is equal to del S sub B del U sub B at equilibrium. That's the definition of it. Okay, and that motivated us to come up with the identity 1 over temperature is equal to del S del U at constant number of particles in volume. Alright? Now, that was a bit of revision and you're probably getting bored, you may even have skipped that. I do have one small bit more revision to do. And you'll see in a moment why I'm doing this, because the thermodynamic identity just falls right out of this. The next thing is, if we allow the system to exchange volume, that means that dV is not 0. Okay? Well, what happens, how do we get into equilibrium if the system now can also exchange volume? Because in the past we just assumed that it was in equilibrium when del S del U, we'll say del S total del U sub A was 0. That didn't take into account anything to do with volume. Now what we're saying is that we'll say that del S total del V sub A also has to be equal to 0, because we now also have this exchange of volume property. Okay, so look, applying the same logic, the exact same logic as I showed in detail there a moment ago, we have the rate of change of the entropy in A with respect to the energy in A is equal to the rate of change of the entropy in B with respect to the energy in B. And similarly, we have del S sub A del V sub A is equal to del S sub B del V sub B, like that. That's in equilibrium. Okay, so that's when our del S versus U graph and S versus V graph stop changing. So, but if we look at it, del S del V, well, what units does it have? Well, it has joules per Kelvin per meters cubed, like that. Joule per Kelvin per meters cubed. But we know that work or energy is equal to force times distance, F dot dx, or we'll say work is the integral minus the integral of F dot dx. So that means basically, if we just look at the units here, we're going to have the following. We're going to have Newton meter per Kelvin per meters cubed, if you want to put it that way, and that's going to be Newton per Kelvin, like that, over meters squared. But if we look at that, well, what has those units? It's pressure over temperature. Alright, because we subbed in for the joule. Okay, so we subbed in for the joule here like this. So this Newton meter, that was the joule. Alright, so basically del S del V has units of, which correspond to temperature divided by pressure. And that motivates us to come up with a new definition for pressure and say that temperature multiplied by del S del V, a constant number of particles and constant energy, is equal to pressure. Okay, now we're ready to derive our thermodynamic identity. So I suppose really this just comes from properties of derivatives. Because we know that we'll say, let's say A is a function of B, C, and D. Well then, dA, just by the properties of derivatives, is del A, del B, del A, del B, del B, plus del A, del C, dC, plus del A, del D, dd, we'll say. Okay? So that's for any number of variables that you want. So what we found so far is that in equilibrium, where we can exchange volume, that entropy is a function, we'll say is a function both of the internal energy and the volume. So that motivates us to say that the infinitesimal change in the entropy is going to be del S del U du plus del S del V dV. But we saw a moment ago that we can rearrange, we can sub in for these derivatives. So that says that we're going to have 1 over T du plus P over T dV is equal to ds. Alright, just to remind you, I suppose I may as well write them here. And we also had T times del S del V is equal to P. Alright, so I subbed both of those in, and we get the thermodynamic identity says that the infinitesimal change in the internal energy is equal to temperature times the change in entropy minus pressure times the change in volume. And this is the thermodynamic identity when you're in mechanical equilibrium. Alright, so thanks for watching. Please pass it on to your friends, subscribe to my channel, and you might also visit universityphysicstutorials.com.